Hey class, it's Travis Bledsoe with you again. I'm going to cover our next section in our mechanical transmissions class, which is basic principles of mechanical systems. So science has discovered there are 6 forms of energy, and we're going to be talking about the first one, mechanical energy. So mechanical energy has 2 elements. You've got kinetic energy and potential energy. So kinetic is any energy that's in motion. The potential is if it's staged but not in motion. Uh, Examples for the potential energy: think of a compressed spring. Um, it's not moving, but it does have the potential for energy. You walk into a room and the room's dark. You've got a light switch there. So you've got a potential at that light switch for energy. When you flip that on, then that potential energy becomes kinetic energy. Or compressed air in a tank, that's potential energy. It's not doing anything, it's sitting there, but it's ready. It's charged and has some force behind that. So back up to kinetic energy, energy that's in motion, is think of like fluid flowing. You can hydraulic systems is a good example. More simple example would be your water hose connected to your house water source, and you've got fluid flowing through that. That is a kinetic energy. So if you've got a sprinkler system at the end of that water hose, if it's a mechanical actuated type sprinkler head, so that water flow, that pressure, that force, energy is going to be doing the mechanical action in that sprinkler head. Other examples of kinetic energy you think of may relate is automobiles traveling down the highway. They have a lot of energy that's in motion moving down the highway, as well as a bullet shot from a gun. So mechanical force, that's force applied to a linear object. It's a push or a pull applied to an object. It's a linear object in this case. We'll talk about torque, which is rotating objects, rotating force. It's next. So force, again, is push or pull applied to an object. It's measured in pounds. It has 2 components. It has a magnitude, which is the mass of the object, and acceleration. And then it has a direction it's going in. We've got a lot of formulas throughout this section, so we'll just take those one at a time as we get through those. So torque, I mentioned, it's a force, but it's in a rotating system, rotating direction. So the example I like to use is like torque wrenches. We've used those in the lab and in our last meeting for hand tools section. So that's a good example of torque. It's a torque wrench and you're turning it in a rotating fashion. You can increase the amount of torque by increasing the lever arm. So there's a formula there to calculate your torque is your force in, how much you're applying, and it's the length of the lever arm. So I've drawn out an example there in the bottom right, kind of showing you maybe a picture of what I'm trying to explain. Like you got a 6-foot torque wrench, and you grab it in the middle. So there's a handle there, and you're really just using 3 feet of it. So I mean, the other 3 feet beyond that does not matter. If your force is being applied at 3 feet, that's just like having a lever arm that's 3 feet long. So if our force in that we're applying with our hand, either at the 3-foot mark or the 6-foot mark, is 20 pounds of force, if that's all we're applying, we're going to measure that amount of torque being applied at that bolt head or that nut, whatever that is. We'll see how much torque we're able to apply with just 20 pounds of force from our muscles, from our hand. So what we take is the 20 pounds of force, and we see the distance between when we're applying the force, like section A, position A, is at 3 feet from where the torque's being applied. So we multiply the 20 pounds of force times the 3 feet. We get 60 foot-pounds. And the foot-pounds come from the unit of measure that we just used. So we use 3 feet, so that's the foot part. And our measurement and our force is pounds, so it comes out to foot-pounds. Now that can be translated into other, can be through calculations to get a different, like inch pounds or Newton meters, but it comes from the distance. You may be using meters or inches. If you're using inches there, it would be 36 inch pounds at that distance, instead of 3 feet, be 36 inches. So you'd be multiplying the 20 times that. If you use meters, you're going to have a metric output. And if you use newtons, say, as your force, then you're going to have newton meters. So there's a lot of different ones you'll hear. Some of the videos I have as a reference, I think some speak in newton meters. That's all it is just a different unit of measure. And they can all be calculated or figured out through different calculations between the two. So 6 foot, if you move out to this position B, we got 6 feet out from the torque being applied. And if we're applying 20 pounds of force, our torque now is at 120 foot-pounds. So we've doubled our amount of torque by doubling the length of our lever arm. So we're taking 20 pounds of force, multiplying it by 6, and getting 120 foot-pounds. So that's an easy way to gain a mechanical advantage. And that's why a lot of people, if they're using a short ratchet, will put like a piece of pipe on the end. They're gaining a mechanical advantage, and that's not a safe way to do it. But that's why they apply like we call a cheater bar. We slide that up on there to gain a mechanical advantage. I do not recommend doing that because tools are designed to handle a particular amount of force. And if you take a power bar or a ratchet that's only designed, for so much torque, and you add a cheater bar on, you're multiplying that torque force through that wrench or ratchet or power bar. It's not designed to handle that, so it's likely to break and injury can occur. So I'm not advocating that at all. It's just why people use the bar on the end of something to gain mechanical advantage. Okay, torque. So we're in a rotating fashion, rotating mechanical system. It's mechanical power transmission components primarily operate with the rotary motion. Torque is in a twisting effort around its own axis. Torque is the force multiplied by the length of the lever arm. Therefore, torque is doubled if we double the length of the lever arm without changing the force. So that's exactly that picture here on the bottom right. So we've doubled the length of our lever arm and we've doubled our amount of torque. And that goes to bullet 3 on this slide. And again, I talked a little bit about the units, and hopefully I didn't get too far out in the weeds on that. But the unit of measure can vary slightly on that. So mechanical work. We're going to calculate our work is by the force applied times the distance that an object moves. And this is again in a linear fashion because there's one for rotating. So here's an example for that. We've got a 100-pound box. So that is a force. Gravity is pulling down on that box, and it's 100 pounds of force to lift that box. I'm going to lift that box 12 feet into the air. So we're going to plug that those two numbers into our formula, which is the force applied, F times D, and the distance is 12 feet. We're going to get 1,200 foot-pounds, so it's 100 pounds times 1,200 foot-pounds. That's our units we've had. We're moving in feet and we're lifting in the massive pounds. So 1,200 foot-pounds of work is done to lift that 100-pound box 12 feet. We'll come back to this example and add one more element. later, talking about the time it took to do that. We'll see that example again. Mechanical work, we've got in a rotating mechanical system. This is mechanical work in a rotating system. So we've got the work equals the um, torque applied times the angle in rotation in radians, or rad. So that's probably not a common unit of measure that a lot of people know, understand, or use. I put a good example. It's an animated one there in the bottom right, and it plays over and over. So we've got a radius there. We drew out the circle. So here's our radius. We'll take that radius and apply it to the circumference. So there's 1 rad. We're going to double that and get 2 rad. So this is just taking your radius of your circle and laying it across the circumference. So we've got 3 rad, and here's we get 3.14. That's where we get pi. That's where the pi comes from. It's 3.14 rad. So you use that to plug into your formula of the force applied, the torque, which is your force applied, and then your angle of radians, or rad. That example came from Wikipedia. So we're going into mechanical machines now, 6 simple machines that help us gain a mechanical advantage. So simple machines are used to produce a mechanical advantage. And mechanical advantage is the ratio of the input to the output. As you can see there in the formula, output force over the input force gives us the mechanical advantage. We'll be talking in theoretical mechanical advantage because friction always adds in a little bit force, a little bit of force. We'll talk about friction too, but when we do our calculations, we're not going to figure in friction because there's always friction in pulley systems and such that gets your actual mechanical advantage. And we'll look at that in a few minutes. So here's some examples of levers that we're going to study a little bit. We're going to be on pry bar, shovel wrench, wheelbarrow. That's all examples of levers. So you may not think of a wheelbarrow as a lever, a lever. But it really is. And you'll see in coming slides of how that applies. Two purposes: levers provide mechanical advantage and change the direction of the applied force. So we've got 3 classes of lever arms. We've got first, second, and third class lever arms. So your first and second is going to be your more, I guess, efficient means of lever classes. So if you look at, just to mention a wheelbarrow, let's start off with that. That is a second class lever arm. So picture that the wheelbarrow being the middle example there in this slide. The fulcrum is your wheel on your wheelbarrow, so it's on the ground, and then you've got your barrel part that we call this holds the load. You put your dirt in that, so it is between the load is in between the fulcrum and the force. You see that you got your load in between your fulcrum and force. So that is a wheelbarrow is a second class lever arm. It gives us a good mechanical advantage. If you look at the first class lever example, you've got your fulcrum in the middle. Now you got your fulcrum in the middle of the load and the force. In our third class lever arm, you've actually got your force in the middle of the fulcrum and the load. So that's your least efficient, but there are some classes of that, like steering wheel and things, of how that works of your third class lever arm. But your first and your second are the most efficient. we can do calculations on this, and the length of the lever arm really determines how much mechanical advantage that we gain, or how much force we have to apply, or how much extra load that we can carry or lift using our lever arm. So this is just an example I drew up. You notice the formula there in the middle. You've got Fe equals FL times DL divided by DE. So let's look at what those mean. The FL um, is your force of your load. It's in the top left. FL is going to be your box, 200-pound box. That's your load. So that's force of the load. We've got a distance of the load. That's your DL. So here our distance, meaning our distance from their fulcrum, is 2 feet. So that's the distance of our load. So our next given is 10 feet. And then there's our DE. So that's the distance of the effort. So our effort's going to be what we're applying. So what we're going to try to find here is Fe, the force of the effort. How much effort do we need to apply? How much force are we needing to apply to lift that 200-pound box? So our force is being applied at 10 feet from that lever arm, but that box is 2 feet from on the opposite side of the lever. We use that formula to plug in these numbers. We've got to have three of these numbers, three of these placements here to get the fourth one. So you can have any of the three and calculate the missing one. So this just so happened to, we're looking for the effort that we need to apply, the force applied by our hands pushing down. So if the FL is given 200 pounds, it's at 2 feet from the fulcrum. So we multiply that by 400. I'm sorry, multiply that, and that is 400. 200 times 2 is 400 pounds. And then our distance, the effort we're applying, is at 10 feet from the fulcrum. So we're going to divide that 10 back into 400 and get 40. So we only need to push on the end of that lever arm at 40 pounds of force to lift that 200-pound load. So you can see that if you change the distance of the effort, either increase it. If you increase it, your force is going to get less. If you decrease it below 10 feet, you're going to apply more force to lift that 200-pound box. All right, we'll look at pulleys. Pulleys are simple machines, and we'll mainly be talking about the pulleys as we do our calculations and such. Pulleys that are in a more applicable setup, which is where you're pulling down on the rope. You've got your fixed pulley overhead. There is an example where you have the moving pulley down at the bottom. And in this case, it's typically not a practical way to lift, because you would have to be above the load. So you have to be pulling up. But there is a mechanical advantage that we want to show you here. And there may be some practical applications in the real world where this would really be useful. So as you see, we've got the first and the second examples. We both have single pulleys. And if you notice there at the top, it says the pulley is called a sheave in industry, a sheave or a sheave in industry. And you get a combination of all of these. You get a combination of the rope or cable, and with a pulley, it's called a block and tackle. That's again repeated on the next slide, but we'll go back to the examples, first two on the left side. So we've got a cursor to get on here. So we've got the fixed pulley overhead, and we're standing beside of the load. So if we're pulling down on this rope, and it's all in relation to gravity of how we're pulling, okay? So gravity has got full control over that weight. So this pulley is really not giving us any mechanical advantage because as we pull down, we're having to pull the same amount of the weight that load weighs. Keep losing my mouse here. Sorry, guys. Um, so number one, the first example here is only giving us a mechanical advantage of one, which is 1 to 1. There's no mechanical advantage at all. So as we pull down this, if that load is 100 pounds, we're pulling 100 pounds to lift it. All it is changing the direction that we have to pull. We can stand off the side and pull it. Um, there are applications for this as long as it's not an extremely heavy load. So we take to the second one. We've got the pulleys mounted onto the load. Now we call this a movable pulley, where the pulley at the top is fixed. Now this one's actually going to move as the load rises. So if we pull up on this rope, as we pull up on the pull rope, we're actually pulling and holding part of that load, only half of it, because the rope on the left side of that is supporting half of the load from the ceiling. As we pull this up, we're only having to pull half the weight. So if it's a 100-pound load, we're pulling 50 pounds, and the ceiling is supporting 50 pounds. So that's how that works. We've got a mechanical advantage now of 2. So if you're pulling down on the rope like the first one, you can count the number of ropes to get your mechanical advantage, but you've got to count the ropes that are being supported. So we've only got 1 rope supporting the weight. You do not count your pull rope if you're pulling downward. If you're pulling upwards, you do count your pull rope because you're now pulling against gravity. And again, it's going back to gravity being our resistance, which is pulling back against it. So we move on to example 3. We're pulling down on this rope, and we still have just a mechanical advantage of 2, but what we have is 2 sheaves. We've got a fixed and a movable. If you count your ropes that are supporting the load, not your pull rope if you're pulling down. So you've got, mouse went away there, rope number 1, rope number 2, they are supporting the load. These 2 here. And then our pull rope is not supporting the load because we're actually pulling down against gravity. So what we're going to have to do is pull down on this, but we've got 2 ropes supporting the load, so we're back to mechanical advantage of two, which if it's a 100-pound load, divide that by 2, and we're pulling 50 pounds. So you can look at example 4, which is a mechanical advantage of 3. You're pulling up. So you do count that rope as your supporting load because you're pulling up against gravity. So you've got 1, 2, 3 ropes in that scenario. Okay, I'm going to stop with the pulling upward examples because everything we're going to talk about going forward is going to be in a more practical application to where you're pulling down on the rope. So if we look at the example 5, we've got 1, 2, 3 ropes that are supporting the load, and we're pulling down on this one, so we don't count our pull rope in this situation. So we've got three ropes supporting the load, mechanical advantage of 3. Let's skip over here to example 7. It's about in the middle. So we've got a mechanical advantage of 4. That's what these numbers and the weight means. So we've got 4 ropes that are supporting the load. Now one in the middle is kind of hard to see, but it's actually 2 ropes. 1, 2, 3, 4. So that's mechanical advantage of 4. And then we're pulling down on the rope. We do not count the pull rope if you're pulling downward on it. Another way to look at this real quickly is to count your number of pulleys. If you're pulling down on the rope, count your pulleys. You got 1, 2, 3, 4. That's another quick way if you're pulling down on the rope. I have to stress that. Next slide. All right, in red there, block and tackle is a system of 2 or more pulleys with a rope or cable threaded between them, usually used to lift or pull heavy loads. So it's kind of a repeat of what we just saw. So we're pulling down on the rope. This gentleman on the bottom left is lifting a 100-pound load. He's got the mechanical advantage of two by having a rope fixed to the ceiling, coming down to a movable pulley, and then the second rope here um, is threaded over another sheave, which is fixed at the top, and it's holding part of the weight. So we've got 50 pounds pulling here, and 50 pounds pulling here, and so the gentleman's having to pull down 50 uh, pounds of force to lift a 100-pound load. So off to the right side, just to repeat again, we got a 1-to-1. If it's got a 100-pound load, you got a mechanical advantage of 1 over this sheave. You're having to apply a 100-pound force to lift it. If you got a mechanical advantage of 2, you got 2 ropes supporting the load. We're pulling down on the rope. We're lifting a 100-pound load. We're having to apply 50 pounds of force. Good videos that reference videos I've got listed in the videos Word document that I'll post on the D2L that you go through. Inclined planes. Inclined planes are slanted objects, and I like to use the example. I relate to it really well. Maybe others do. It's like using boards to put on your tailgate of your truck to push your lawnmower or maybe a motorcycle or something up in. So if you've ever done that before, or if you've not, then you can just kind of imagine if you've got short boards, you're going to have to push a lot. You're going to have a lot of force and effort to push. But if you get longer boards, the long as you can, then you don't have to push as much. But what's your trade-off? Your trade-off is your distance you're traveling. So you're having to travel a further distance, but you're having to use less effort, which is often the case that we want is, to reduce that amount of effort, even if we have to travel further on those longer boards. So that goes into that red sentence there. The work done remains constant. So regardless if you use short boards or long boards, your overall work when you do the calculations of the distance traveled and force applied, remains constant. But our force applied is going to decrease as we increase the length of our boards. If that makes sense, increase the length of the inclined plane. So read that statement straight out as the work done remains constant, but the effort or force required decreases as the distance increases. So mechanical advantage, there's no machine that's 100% because what we've talked about, like pulleys, the 1-to-1 ratio, even if you got a 1-to-1 ratio, you're going to have to pull a little bit harder to lift a 100-pound load on a 1-to-1 ratio because you've got friction built into that pulley system. So we use bearings, different types of material to help reduce that, but in real world use, you're going to have friction there. So like I mentioned earlier, we're going to talk about our theoretical mechanical advantage in our calculations, but the actual mechanical advantage is introducing the friction, which we kind of get into next couple slides. So theoretical mechanical advantage versus actual mechanical advantage. You've got the percent efficiency. The actual mechanical advantage is the actual output over the actual input times 100%, where you've got the AMA and TMA. Speed and velocity. So speed, of course, you're familiar with. It's how fast something is moving. And there's a formula to calculate that. You get your distance you traveled times or divided by the time you traveled that. So you're going to divide the time you traveled into the distance that you traveled. And velocity is just speed with direction. If we get into test and we have these formulas on, I give you the formulas on the test to figure out all this. So don't worry about memorizing. However, slide before, you may want to recognize this this formula to see if it's a true or false answer. So, yeah. All right, acceleration. Acceleration is still dealing with speed, and it's how fast speed is changing, the rate of change of speed. So we got a formula for that. I got a formula for everything. So we got a formula for acceleration. It's the final speed minus your initial speed divided by the time elapsed. So you're starting out at a certain speed, and then you increase your speed. You hit the pedal to the floor, and you increase your speed from 30 to 60, and then however long it took you to change from 30 miles per hour to 60 miles per hour, that is your acceleration. So you divide your time into that distance, or the speed change, which would be 30. 30 to 60 is still 30, and the difference. So your time elapsed is divided into that 30. Rotational speed, speed of an object around its own axis, measuring revolutions per minute. So we deal with RPMs a lot. Most cars today have an RPM gauge. So on your vehicle, and if you're not familiar with what that is the crankshaft in the engine. When the crankshaft in the engine, typically in the bottom of the engine, we're looking at how many times that thing rotates within a certain time frame. And we typically use minutes. How many times does it make a revolution per minute? So we see RPMs on our dashboard. That crankshaft is turning maybe 2,000 RPMs. That's 2,000 times per minute. So to calculate that, you've got your angular distance and revolutions. So how many revolutions does it turn over a time elapsed? Easy to calculate. Your speedometer or your dashboard's basically doing that for you. That there are industrial applications that you'll have to apply this when you're looking at gearbox speeds and such, that you look at how many revolutions it takes and how many minutes it takes to do it, or seconds, and it's time elapsed. So you wouldn't express it in RPMs if you measure it in seconds. It'd be revolutions per second, RPS, or revolutions per hour. So you have to use express it in the unit of measure that you measure it in. So mechanical resistance. This is I guess the opposition to what we're trying to get for mechanical advantage. This is the friction is working against your mechanical advantage. So it results in energy loss, generation of waste heat, it wears on parts. The main reason is your surface finish. So the smoother the surface can be, the less friction you're going to have, or if you can use a good lubrication to help make the surface smoother. So if you've got a coarse or rough surface, then your friction is going to increase versus a smooth surface. There's two types of friction, and don't get these confused with what we talked about earlier in motion. We've got static friction and kinetic friction. Static friction is always greater than your kinetic friction. Kinetic is your moving friction. It's amount of friction that I'll just say you're pushing I don't know, everybody's probably done this, a heavy cardboard box across the floor. Well, it's all going to depend on what kind of floor you're sliding on. If it's carpet, typically it's not too bad. If you're on hardwood, you get a little bit more friction. If you're on tile, maybe a little less. But we'll say we're on a vinyl floor, which gives a pretty good amount of resistance to cardboard. So when you start to push that cardboard box across a vinyl floor, you remember if you remember doing it, it's harder to get it started. And it's one of those things, if it's really heavy and it's taking all you got to push it, it's you realize that once you get it moving, it's not as hard to keep it moving. So you don't want to stop. That's an example of your static friction. To overcome that friction of sitting still from going from static to kinetic is a greater deal of push. But once you get it started, kinetic friction is less. We've got charts to look in the next couple of slides to calculate, because everything's got a coefficient of friction, which leads us to this slide. It's a ratio between the force that is required to move an object and its weight. So, your biggest variable there is your weight of your object. Then you've got the surface finish, and some surface finishes are going to be less conductive to the friction. Um, so we need to know the friction coefficient of friction of that, which is the force applied and the force applied down. I'm sorry, force applied from, in this example, from the left to the right, and then your weight pushing down. Coefficient of friction. If you notice, your force is applying from left to right, but it's got an arrow there of your friction pushing backwards. So that's really your resistance that's actually going against what you're trying to do, is push the box across the floor. The box being the green object, and your surface or floor is being your kind of tanned object in that picture. So here's a coefficient of friction table. This table can get extremely large. So this is just only some examples. And what I'm going to do is on the test is just give you one of these examples is in the left column. I want you to just give me the example, the answer that I request. So let's look at the chart first. All I really want you to know how to do is read this chart. So you got the material on the left column. It's whatever type of material sliding on a different type of material. So we move out to the next two columns, which is both the static, it's stationary, sitting still. Like I said, it's going to be a um, higher friction level. Move out to the last two columns are in sliding motion. These are kinetic, actually in motion. So in both applications, we've got a column for dry or lubricated. So that makes a difference too, of course, if you've got a dry surface versus a wet surface. And what is the wet surface? Is it water? Is it oil? So that's a variable too. So let's look down to show you how to read the chart. It's a rubber tire on pavement. If you drive a car and you want your tires to grip good. So this is showing your rubber on pavement of your static dry application. You got a 0.8 to a 0.9 coefficient of friction. So let's look at that same dry application when it's sliding. So when your tires become skidding or sliding on the pavement, come over to the, I guess the fourth column of that would be the sliding dry. You got 0.75 to 0.85. Well, that's slightly lower than your static friction. So that's how your kinetic or sliding friction is less than your stationary. And then of course you got your the other column of the lubricated of static and sliding, and that asterisk is referring to wet pavement if it's just water on the road. And your static again is greater than your kinetic. Excuse me. All right, mechanical power. This is the rate of doing work. The rate of doing work. So we talked about work earlier and then calculations of that. So we're going to bring back an example we used earlier. So power is the work done, the W, divided by the time it took to accomplish that work. You remember our example earlier, we lifted a 100-pound box 12 feet in the air. So down the bottom right-hand corner, I've listed that formula for work again. Remember, your work is your force times the distance traveled. Force being 100 pounds, distance traveled being 12 feet. We had 1,200 foot-pounds as our work. So now we're going to throw in another element of how fast did it take us to lift that 100-pound box 12 feet. So in this example, it took 10 seconds. So if a 100-pound box is lifted 12 feet in 10 seconds, what is P? So the powers is your work divided by time. So we've already calculated work in the previous section. So we've got 1,200 foot-pounds of work and divided by 10 seconds, and we're going to have 120 foot-pounds per second is what our power equates to. 120 foot-pounds per second. So here's some additional resources in this PowerPoint presentation. I'm going to list these on a Word document along with a link to this video. I guess if you're watching the video, you've already found it, but like I have in the past, just put the link to the Word document or the PowerPoint presentation. I'm sorry, link to the YouTube video into a Word document. And I'm also going to put these additional resources in. I do want you to watch the ones listed as required viewing. The simple machines of pulleys, and then hopefully these links work going into Khan Academy. The guy that does Khan Academy's got some good stuff there, and to kind of shorten it down, I got a start at and a end at time here. So that's parts I want you to catch. And these are talking about the mechanical advantages of levers. And this top section is talking about mechanical advantages of pulleys. Certainly watch that first one there. So we've got questions. We'll get together for lab soon, and we'll do our precision measuring lab and do our test after that. Hope everybody's doing well, and I'll talk to you later. Email me with any questions or concerns. Thank you.